What's up, Raiders? Continuing our discussion of one-dimensional motion problems. So if you take a look at number 13, determine the stopping distance for a car with an initial speed of 90 kilometers per hour if the acceleration, and again, in everyday life we might say deceleration because it's slowing down, if the acceleration rate is negative 4 meters per second squared and human reaction time of 1 second. So in an earlier video, you can go back and watch part 1, this initial speed or initial velocity of 90 kilometers per hour, we've already shown how to do that conversion, is equivalent to 25 meters per second. So we're going to use meters per second here to be consistent with our other units. Now, in this scenario here, the human reaction time, that hasn't shown up in a problem before. So if you think about that, as the car is going down the road, it's going 25 meters per second. And there's going to be some block of time between when the driver sees something that makes them want to stop and when they actually put their foot on the brake. So when you see the human reaction time of 1 second, really all that means is there's going to be 1 second of the car traveling 25 meters per second before you ever actually hit the brakes. So that's just the constant velocity scenario there. So if the car is going 25 meters per second and it takes 1 second to process, okay, there's a reason I want to stop up ahead, so I'm going to hit the brakes. You're basically just going 25 meters per second for 1 second. So really at the end, we're just going to tack on an extra 25 meters. That's part of the reason that speed limits are important is, before you even hit the brakes, you've covered some additional distance when you've seen something that's made you need to stop, whether it's a person in the road, stop sign, whatever it might be. So let's identify what information we're given. So that initial speed, so they actually kind of hit you over the head with it here, that's VI as opposed to plain old V for constant velocity. So initial velocity is 25 meters per second. And since they said determine the stopping distance, we know that the car is going to end up with a final velocity of 0. And then the acceleration rate, generically, or you could also use the terminology deceleration, is negative 4 meters per second squared. Again, these are vector quantities, so direction matters. We indicate that with positive and negative signs. So if the initial velocity is positive, you need a negative acceleration to stop. So we want to find the stopping distance, displacement. So this specific combination of variables we can analyze with VF squared equals VI squared plus 2AD. So we want to isolate the displacement, get it all by itself. So I'm going to subtract VI squared from both sides. VF squared minus VI squared equals 2AD. Well, displacement is being multiplied by 2A, so divide both sides by 2A. So we're going to end up with our numerator, VF squared minus VI squared will be 0 squared minus 25 squared over 2 times the acceleration of negative 4. So notice what's going to happen with our signs here. Our numerator is going to give us negative 625. Our denominator is going to be negative 8. And a negative divided by a negative will give us a positive displacement, which makes sense because if the car's initial velocity is positive, then the displacement it's moving in that direction should also be positive. So this ends up being a displacement of about 78.1 meters. Now, that's how far the car traveled while you were physically hitting the brakes, slowing down at 4 meters per second squared. But remember, because of the human reaction time of 1 second here, you were going 25 meters per second for an entire second without actually hitting the brakes. So in terms of determine the stopping distance, you also need to factor in when your brain processed the fact that, okay, I need to stop here, you went an additional 25 meters just in that processing time to when your foot actually hit the brakes. So the displacement is actually the 78.1 meters you went while your foot was physically on the brake, plus an additional 25 meters you went. So it's approximately 103.1 meters. That's actually how far you went once you recognized that you needed to stop. Okay, and we had already solved 14 together in class. Now if you look at 15, 15 looks pretty overwhelming, but this is a perfect example of what we've talked about before, taking a complex scenario and breaking it into smaller parts. So you see here, a person driving his car at 50 kilometers per hour approaches an intersection just as the traffic light turns yellow. He knows that the yellow light lasts only 2 seconds before turning red, and he's 32 meters from the near side of the intersection. Should he try to stop, or should he punch it and try to get through the intersection before the light turns red? The intersection is 15 meters wide, and the car's maximum deceleration rate is negative 6 meters per second squared, whereas it can accelerate from 50 kilometers per hour to 70 kilometers per hour in 6 seconds. Ignore the length of the car and his reaction time. So this problem is overwhelming in terms of the amount of information you're given. And if you try to process everything all together, it's just going to be too much. So again, with the idea of trying to find ways you can break problems apart into smaller, easier to analyze parts, you have two scenarios here. The car either stops in preparation for the light, or they try to accelerate to get through the light and get through the intersection before it turns red. So that's how you break it apart. Analyze each one separately. Now, in terms of where to start, I mean, technically it doesn't really matter if you analyze the scenario where they try to stop or they accelerate. It doesn't really matter which one you analyze first, but thinking in terms of general safety, I would think the default thing to think about would be, okay, it's most likely that it's safer to try and stop rather than speed through the intersection. Anything that looks like it might be a scene from an action movie, that probably shouldn't be your first choice. So let's just focus on when the car tries to stop, and let's see where that takes us. And if the person can successfully stop, you're done. You don't need to worry about any of the other things going on. But if they cannot safely stop, because that can happen, then we would need to analyze the next part of the scenario to see if they can safely get through the light by accelerating. So let's see what we're dealing with here. So a person drives his car at 50 kilometers per hour. So immediately we got to convert that to meters per second. And in the part 1 video of this series, I showed how to do that more specifically. So I'm just going to go through it quickly here. So 50 times 1,000 times 1 times 1. So our numerator is 50,000 meters. And 50 kilometers per hour is really 50 kilometers per 1 hour. So 1 times 1 times 60 is 3,600 seconds. So equivalently, this person would go 50,000 meters in 3,600 seconds. So this is equivalent to about 13.9 meters per second. That's that initial velocity. So again, we're going to analyze this person stopping. Now, as the problems get more complex and you can break them up into smaller parts or you can analyze in different ways, it becomes increasingly more important for your own sake and for documenting it for the teacher that you clarify what segment of the problem you're analyzing. So I'm just going to put a simple label of stop. That's your way of communicating to me, all right, Mr. Dubois, anything I'm doing under here is to analyze the scenario where this car stops. So the initial velocity is approximately 13.9 meters per second. And let's see what else we know here. Focusing on the fact that we're going to analyze the stopping scenario. He knows that the yellow light lasts only 2 seconds before turning red, and he's 32 meters away from the near side of the intersection. So you can actually go a couple different ways with this. If we're analyzing stopping, final velocity is 0. And we're told the car's maximum deceleration rate is negative 6 meters per second squared. So let's add in that acceleration rate of negative 6 meters per second squared. And again, notice vector quantities, direction matters. So an initial velocity that's positive would be slowed down by a negative acceleration working against it. So we can do a couple different things here. We can figure out displacement. Now, if you look in the wording of the problem, you're already told how far the speeder is from the light, 32 meters away. But if we analyze this with VF squared equals VI squared plus 2AD, we can figure out what's the car's stopping distance. Because you could certainly have a scenario where the displacement here that you end up with, if you're slowing down at 6 meters per second squared, it might take you longer than how far away from the light you are in terms of the amount of road that you need to stop. So obviously it's not safe to have a situation where you're stopped, but you end up in the middle of the intersection. So let's see how this compares to the fact that we're 32 meters away from the light to begin with. So we're going to solve for displacement. So I'm going to subtract VI squared from both sides. VF squared minus VI squared equals 2AD. Divide both sides by 2A. So right off the bat, if this displacement that we're going to calculate here, if it's going to take this person more than 32 meters to stop, then that's a good indicator that's probably not safe to try and stop because they're too close to the light to safely stop before the light. So let's see how this compares to the 32 meters away that they are. So 0 squared minus 13.9 squared. Notice that's going to give us a negative numerator. And the acceleration, 2 times negative 6, that'll be negative. So negative divided by negative will give us a positive displacement, which it should be, because that's consistent with the fact that we have a positive velocity. All right, so moment of truth here. Okay, so this is encouraging. So the displacement is 16.1 meters. So the car only needs 16.1 meters to come to a stop. So the car can very comfortably stop before the light turns red. And so let's just kind of see, so based off of that fact, you know you can safely stop before the intersection. So we can kind of continue on that path. That seems like it's a safe move. So now let's just take a look at how much time it's going to take this car to stop. So again, indicating that you're analyzing the stopping scenario rather than the speeding up scenario. So we've really got the same information we had before. Initial velocity is 13.9 meters per second. Final velocity is 0. The acceleration rate's negative 6 meters per second squared, so we can find time. So this specific combination of variables we can analyze with VF equals VI plus AT. We want to find time, so subtract initial velocity from both sides. VF minus VI equals AT. Divide both sides by acceleration. So time the numerator, VF minus VI, 0 minus 13.9. It's going to give us a negative numerator. The acceleration is negative 6 meters per second squared, so a negative divided by a negative will give us a positive time, which it should be. So 13.9 divided by 6 is about 2.3 seconds. And again, always be reflective of the significance of your answers. So this might seem like a little alarm bell to you that, okay, this is a problem because you see the reference to 2 seconds before turning red, and it's going to take you 2.3 seconds to stop. That might initially make you nervous, think something's wrong, but just reflect on what this really means. We already figured out that you can clearly stop well before the light in terms of how far away you are. And if the light turns red in 2 seconds, but it's going to take you 2.3 seconds to stop, that's not actually a problem. All that really means is, as you're in the process of hitting the brakes and coming to a stop over the 16.1 meters, you'll see the light turn red after 2 seconds, or another way of saying it is about 0.3 seconds before you actually stop. And if you think about it, that's really the most common scenario when you're coming up on a light that's turning red. You hit the brakes, and as you get closer and closer to the light, ultimately it turns red, and then you stop. So in this case here, this is a perfect example of a really complicated scenario with tons of given information. And if you try to analyze it all at once, it's overwhelming. But in this case here, breaking it up into smaller parts, and what made sense here was, all right, well, let's analyze this scenario that typically would be the safer one. And as long as that works, we're done. We don't need to go any further. So the kind of action movie aspect of trying to punch it to get through the light, we don't even need to analyze that. So stay safe out there, Raiders. If you have any questions, contact me on the Remind app.